Hi, in this example, we're going to look at the first law that is for constant pressure device. And let's see what we have here. This is a mass of 12 kilogram and it's at a saturated vapor. All right, so the state one, they already tell us it's going to be saturated vapor. It's R134. And it's contained in this cylinder at P1 equals 240 kilopascal. Now they said there's a heat 300 kilojoule that's added to it, heat coming in, QA, at this constant pressure. So P1 is going to be equal to P2. Okay. Then they have this voltage is 110 volts, and for 6 minutes applied to it, determine the current applied if the final temperature. So they want you to find what's going to be I in amps. The final temperature, so state 2. State 2 is going to be T2 is 70 degrees Celsius. So they want us to find the current that's going through the resistor. All right, so first of all, if you have a problem like this is how logic goes. Is this closed system? Yes, because there's no mass coming through, and it's a piston cylinder, and it's a constant pressure process. And when you have electrical work, when you have also heat exchange, we're going to use the first law. And is this first law constant pressure? Yes, then we'll have a formula just for that, first law constant pressure. So the basic video was the previous one, you can look at it. So the formula for that is going to be the heat transfer Q is going to be equal to delta H plus work others, right? And for this problem, there are other type of work because there's electrical work here. Now let's take a look. Do we know the heat coming to the system? So yes, we do. There's a heat transfer N. So that's going to be 300 kilojoule right here on the left. That's heat coming. Then we need to figure out delta H. Delta H is going to be M times small a delta H. The H2 minus H1. And we also need to have work others. And now this work others, we need to make a note. That's going to be think about the sign convention. The sign convention for work is work being positive. It is when the work done by system. If it's work done to the system, then that's going to be negative. And here it's work done to the system, so that's going to be negative value. So we're going to be, for this work others, going continue, so it's going to be negative. And this electrical work, so electrical work, I'm going to do a quick review on that. You learned it's going to be voltage and times amps times time. That's going to give us the electrical work. So here, if we use I using amps and V use voltage, T here have to be using seconds. All right, and we're trying to solve this amps. So what? Write down I. That's what we're solving. The voltage is 110, and the time it's 6 minutes. 6 minutes is 360 seconds, right? So then with that, that's going to give us the unit of joule. Then be careful with the unit. Here, what do we have? We have in kilojoule. This gives us in joule. So we have to divide by 1000. Then that would give us the unit of kilojoule to make sure we have the same dimension. So far, we're just brainstorming using this governing equation for first law for constant pressure. And we know the heat coming, it's 300 kilojoule positive, it's heat coming. And we know the work others. And this work others is work down to the system, so it's negative. And we're solving I, current. So the only thing we need to solve is going to be the H2 and H1. How do we find H1? So we know for state 1, we know it's a saturated vapor and it gives us pressure. So from here, we can certainly figure out our H1, right? That's our brainstorming process. Then the state 2, we know one property. We know the temperature. What's the second property do we know? That's right, constant pressure. It's a constant pressure process. P2 is equal to P1 equals 240. So knowing those two, we can figure out our H2. That's where we're going. So go ahead, look at finding H1, because for state 1, we know it's saturated vapor and P1 is equal to 240 kilopascal and saturated vapor. Then our H1 is going to be vapor, so it's going to be Hg, not Hf, since this is saturated vapor, at 240 kilopascal. And this is in SI unit, however, it's on 134. So we're going to go to the right table. We're going to go to Appendix 1, and we're going to look at table A12. It's our pressure table. At 240 right here, we are reading out our H this time, right? We're reading out Hg to be more exact. So that's 247.28. So that's going to give us, right here, 247.28. That's going to give us Hg in kilojoule per kilogram. So we find our H1. That's our table A12. Now we're going to look at state 2. State 2, it's going to be same pressure, since it's constant pressure process. But this time we don't know what phase it is. Earlier we were told it's saturated vapor, but this time we do know the temperature is 70 degrees Celsius. So the first thing we need to determine what phase that is, right? So go 240, we're going to go to the pressure table. So from table A12, we're going to find what's going to be the saturated temperature at 240 kilopascal. Right? Then we're going to use our given temperature 70 degree to compare that with this number. Let's see, 240. At 240, what's going to be our saturated temperature? It's negative 5.38 degrees Celsius. And our temperature is 70 degree, V greater than Tsat. So what does that mean? Which means this is a superheated vapor. So if it's a superheated vapor, we're going to go to the correct table, table A13, and look at this pressure and this temperature, 240 kilopascal and 70. So table A13, let's look at 240. 240 kilopascal, that's going to be what? 0.24. We're so lucky, right? They have 0.24 megapascal millitable. Now let's look at 70. And they do have 70 as well. So look across to 70. And we're reading H value. So it's 314.51. That's going to be our H2 in kilojoule per kilogram. So we found our superheated table, and with this 240 megapascal, which give us 0.24 megapascal, and 70 degree, we found our H2. So knowing those two now, we can go back to this governing equation here. So let's write it down. That's a heat transfer, 300 kilojoule. It's going to be our mass. Mass is given as 12 kilogram here. So it's 12 kilogram. Then times our H2, 314.51 minus H1, 247.28 kilojoule per kilogram. Then minus I times voltage 110 times 360 seconds. That gives us in joule, but we are going to divide by 1000 to give us the unit of kilojoule. Then all the term have unit of kilojoule. We can just solve for I. So let's go ahead, 300. Let's see what we have for this by one here. So here we have 806.76 kilojoule, then minus 360 times 110, then divided by 1000. That gives us 39.6 I. All right, then we can solve for our I. I will be equal to 806.76 minus 300, then divided by 39.6. Let's see what we have. And I have an answer here as 12.796 repeating. So basically that's 12.8 amps. Okay. All right. So we solved this problem. This is a good problem that's showing the essence of first law. If it's constant pressure, then we're using this formula here. Q equal to delta H plus work others. For this problem, there's indeed other type of work down to the system and using sign convention. So here work is going to be negative value. And then we know in order to find this current, so another little sidetrack is electrical work is IVT, and be aware that gives us a unit of joule. So you have to change to kilojoule here. You just need to find, so to solve this problem, we just need to find H1 and H2. That's where we are starting for this problem. And for second property for state 2 is going to be the constant pressure. So that's all for this problem. I'll see you next time. Bye.